In this section, we're going to examine parabolas, some properties of parabolas, and how to graph a parabola given its equation. So let's start with a definition. A parabola is basically the set of all points in a plane which are equidistant from some fixed point called a focus and a fixed line called its directrix. Another way of stating the set of all points is also the locus of points. The locus of points is a mathematical term meaning the set of all points. Let's examine visually what this represents. Below we have a line, the directrix, and a point, the focus. So we're looking for all of the points which are the same distance from each of these. Here's a sample point. Now in order for this point to make up the parabola, the distance from this point to the focus has to be the same as the distance from this point to the line. And if we take the set of all points which satisfy this relationship, we end up with a parabola. Parabolas are very interesting because they show up again and again in nature. Here are some examples. The Golden Gate Bridge in San Francisco follows a parabolic arc for the suspension cables which hold it up. Water shooting out of a water fountain follows a parabolic arc. And satellite antennas also follow a parabolic arc. The reason for this has a lot to do with the properties of the parabolic shape. In considering the suspension bridge, what is happening here, or why this is useful, is that the weight being suspended by one of these cables is balanced with its corresponding cable on the other side, because the weight of this cable being pulled down gets pulled from the focus, and it gets balanced by the weight being pulled down on the opposing side by its focus. So these two opposing weights balance each other out so that a suspension bridge can end up holding very heavy objects. Something similar will happen with the satellite antenna. To receive information from space, the signal often gets dispersed and becomes very weak. But what a parabolic antenna will do is take signal coming in from a large area and bounce it back towards a focal point, so that information coming in from a much larger surface can be more effectively collected. So in the context of what we will be doing with parabolas is understanding how the equation of a parabola relates to the graph of a parabola. These notes can be found on page 10 of your packet. So what we're going to do is to explore the connection between the equation and the graph. So down here we have an equation of the line, or excuse me, of the parabola y equals x squared. So oftentimes when we don't understand how an equation relates to a graph, we'll explore it by plugging in points. Here I have some fixed points I'd like you to plug in to find the corresponding y value and then plot them on this graph grid. I've given you the first one. When x is -3, the corresponding y value would be -3 squared, which is 9. So take a moment to pause this video and fill in the rest of the points. Okay, hopefully you've gotten each of these values. So now the graph of y equals x squared should be the curve which connects each of these points. And you may notice that it follows a parabolic shape. So let's draw in our parabola by connecting these points with a smooth curve. And there's my parabola. Now, as we go through this video and you're taking notes, if you need to pause it at any time to write down what appears on the screen, please do so and then return to the video. So notice that the shape that we have graphed here actually results from y equals x squared. which gives us a parabola. Anytime we see a variable x squared, we refer to this as a quadratic term. Thus, this is a quadratic equation. A quadratic equation is said to be parabolic, meaning that its graph is that of a parabola. There are three forms of a quadratic equation that we will study. The first, and one you're most familiar with, is the standard form. The second is the factored form, and the third is the vertex form. The vertex form is the form that we will be focusing on in this video. We will cover the other two over the course of our study of parabolas. So let's look at some of the details of the vertex form. First, the main thing you can read off from this form is the vertex. The vertex, much like that for absolute value graphs, is the coordinate h, k, and can be read off from the corresponding locations in that form of the equation. Notice that the value of h shares the opposite sign from what it appears in the equation, and the value for k shares the same sign. The other value we can read off is a. A acts like the slope. But it's a bit different. Because it acts like the slope but isn't technically a slope, we call it a scale factor. Let's see how these things relate to our equation of a parabola. If we look back up at our original equation, I'd like to represent this visually with an actual physical graph. So I'm going to switch over to some graphing software. Here we are. So here I have my similar table to what I had calculated on the page of notes, where I have each of my corresponding x values and y values. Okay. Now I'm going to see what happens as we examine our scale factor, this a. So looking at our equation, y equals a times x squared, I'd like to see what happens as I change my a. Now, if you notice, we have each of our corresponding plotted points here on our equation. So this corresponds to the exact parabola we began with in the do now of the notes. Take a moment to anticipate what you believe will happen if I multiply a by 3. If you predicted that each corresponding y value will now be 3 times larger, you are correct. Take note as to how our new parabola compares to the dotted line representing our original parabola. The point which corresponded to x equals 1, which was originally at 1, is now 3 times larger. So what appeared here at 1, 1 is now 3 times larger at 1, 3. The point that originally corresponded to 2, 4 is now also 3 times larger. So 2, 4 is now 3 times larger, so it's taller on the graph. As a result, our parabola seems to have gotten more narrow. If I go back to my original parabola, take a moment to anticipate what you believe would happen when a is negative. If you said that each of the corresponding y values would become negative, making the graph appear to flip over, you are correct. Make a prediction as to what you believe will happen if a is 1/4. If you said you believe the parabola would get more wide, you are correct, because each of those original 3 points is now 1/4 as large as they were before. So how do we use this pattern in graphing parabolas? Well, let's go back to our original graph. Now, earlier I said that a acts like the slope. remember that slope of a line is the change in y over the change in x. Now, unlike slope, in this equation, unlike a line, x values are squared. So what ends up happening is that rather than going over and up in a linear way, the slope of the line dynamically changes as we move along the x values. So how does it change? Well, consider the effect of x squared. In my original parabola, when the a is 1, when I go over 1 in the x direction, I go up 1 squared. When I go over 2 in the x direction, I go up 4, which is 2 squared. When I go over 3 in the x direction, I go up 9, or 3 squared. The same happens when I go backwards. If I go backwards 2 in the x direction, I go up negative 2 squared, which is 4. So unlike a line, which goes over and up in equal amounts, a parabola goes up by the square of its corresponding change in x. Consider what's happening when a equals 2. Now the y value is not just the square of x, it's the square of x times this value a. So when a is 2, I go up the square of x times 2, or 2 times the square of x. So when I go over 1, I go up 2 times 1 squared, or 2. When I go over 2, I go up 2 times 2 squared, or 8. We can exploit this pattern every time we have a different value for a. To sum up, back on page 10, there are some interesting patterns of the quadratic graph. First, it's very similar to the absolute value graph in terms of its vertex form, where its vertex can be read directly off the equation. In fact, the vertex forms look very similar. Also, like the absolute value graph, the quadratic graph has an axis of symmetry which passes vertically through its vertex. The graph is symmetric, meaning self-similar, on either side of that axis of symmetry. The equation of the axis of symmetry is x equals h. Symmetry is helpful in graphing a quadratic equation because we actually only need to plot points on half of the graph. Here I have a quadratic equation written out in vertex form where the a is 1, the h is 0, and the k is 0. If I change h to 3 and k to 2, I see that the vertex has moved to the point 3, 2, and the points on either side of the graph are symmetric, meaning they match up with each other directly on either side of that axis of symmetry. So as a shortcut for graphing parabolas, we need to only graph the points to one side of that axis of symmetry, and then we will have the symmetric points to the other side. We will explore more parabolas tomorrow in class.